To today's class. Let's go ahead and get started on today's lecture. Okay, excuse me one second. Turn my sounds off on my phone to avoid interruptions. Okay, so today we're going to be talking about linear regression. Actually, linear regression is the topic of the week, so we'll be talking about this both today and on Thursday. So we'll discuss a little bit simple linear regression, and we'll be looking at a data set which analyzes advertisement effects between different media like TV, radio, etc., to see what's the most effective. And we'll talk a little bit about linear regression as descriptive statistics and thinking about some of the inferential tasks that we can do associated with linear regression. And then at the end of class, we'll talk a little bit about multiple linear regression and how to extend linear regression to also model nonlinear relationships, which may be present in the data. Okay, so go ahead and check out this introduction to statistical learning, as it's got some helpful information. Okay, so what is linear regression? You may have probably seen this before in some other classes, but if you haven't, that's fine. In a linear regression model, we want to model the relationship between what we call an independent or explanatory variable x and a real valued dependent value y. Okay, so we're interested in making predictions of one variable, which we'll think of as the response variable or the dependent variable, from another variable, which we'll think of as the independent variable or the explanatory variable or the predictor variable. Lots of different words here that are used to mean the same thing. But some examples might be we're interested in predicting a home's price from its square footage. We're interested in predicting profit from advertising dollars spent. We're interested in predicting lifespan from stress. Now you may be thinking, okay, well, you know, these are really complicated phenomena. We probably need more than one factor to model these things. And indeed, we'll talk about that more at the end of class. But one thing to keep in mind as we're going through today's material is that we are talking about a dependent variable that is real valued, okay? So that's quantitative. So for example, if you're thinking about the relationship between time spent studying and whether you pass or fail a course, there's a clear relationship there, but this is not a quantitative response variable. This is a categorical variable. You fail, you don't. So we're not talking about there are for doing those predictions, but that's not what we're talking about today. We will discuss that later in the course. Okay, so here's the basic setup. We're going to assume that we have in samples x1, y1 through xn, yn. So the x's are my predictors and the y's are my response. And we want to model the relationship between them with the most basic relationship we can think of, which is a linear one. So we're going to model y as beta naught plus beta 1x. So beta naught is the intercept and beta 1 is the sign. And we want to find the best values for these parameters, beta 0 and beta 1, and we'll denote them with little hats to denote that we are sort of approximating these quantities, which might be unknown in the population, so that the prediction, y hat, when we predict the values based on that computed line, best fits the data. So let's say we have a point cloud of all these blue points. We want to come up with the equation of that red line that best fits the data. Okay, and so we can define, now here we get into, well, what do you mean by the best line? Because there's various ways of measuring what the best line considered. The easiest thing to do, however, is to say, well, we mean the best line in the least square sense. And if you define what that means in the least square sense, the best parameters are given by the following formulas: beta 1 hat, beta 0 hat, and they're defined from the data value, from the means x bar and y bar of the data. And there's a proof of these formulas. If you look in the note, I'm not going to go in a lot of detail, but I'll leave it for you to read. So here's a little proof deriving why those formulas are the optimal ones. And the basic idea is to consider what we call the residuals, or the errors associated with the line. So if we take each y value and then we subtract off what the predicts, then we get the error or the residual of the line. And we want a method which minimizes the sum of the squared errors. So we can define this function of the two parameters of interest, which has this form right here, and we want to minimize it as a function of beta 0 and beta 1. And so you may remember from your calculus classes that if you want to minimize a function, there's a standard way to do this in calculus, which is take partial derivatives equal to 0. And that's basically, so if you take partial derivative with respect to those parameters of this loss function, because it has such a nice formula, you can end up deriving these exact solutions to the line of best fit. Okay, let me go back here. Okay, and we will, of course, be implementing this in Python. And so some Python packages for regression are stats models, scikit-learn, and scipy. And we'll look both at the stat models and the scikit-learn packages. The stats models one is really good for doing statistical inference associated with linear regression. And the scikit-learn is really good for doing cross-validation, which we'll discuss a little bit in the next lecture. And then scipy is not probably the best option for linear regression, but it has some basic functionality built in. Okay, so let's take a look at some data. So we're going to use the advertising data set. And this consists of 200 data points, which you can think of as different markets, i.e. different cities, different locations. And then for each data point is recorded the number of sales of a particular product, as well as the advertising budget for 3 different media, for TV, radio, and newspapers. And so we'll use linear regression to study the effect of advertising on sales. So sales here is the dependent variable. It's the variable that we want to predict. And the amount of money spent on advertising are the independent variables. And those are the ones that in a real world situation like this one, you could perhaps control or adjust. And this might inform what a good strategy is for the company moving forward in terms of where's the most effective place to spend their money. Okay, so first of all, one of our standard imports and setup. Oh, hold on, I have a few questions that I didn't notice until now. Oh, where slr.pdf? So it should be in the folder, in the lecture folder containing the lecture. Yes, thank you. Somebody already answered that. So the same folder on the lecture folder that has the Jupyter Notebook. Okay, so we'll do, first of all, our pandas.readcsv to read in our data. We'll tell it that the first column, column 0, contains the index values. And then we can take a look at what the data looks like here. So here's TV, radio, news, and sales. Okay, So first of all, it's always a good idea to plot the data so you can get a sense of what you're looking at, perhaps discover any errors that were made when you imported the data or anything like that. So first, let's just take a look at the scatter plot. Here, I'm making a separate scatter plot for each of those variables. So I'm plotting for each independent variable, TV, radio, newspaper, making a scatter plot of that versus sales, but plotting it all on the same axis so we can look at everything at once. Okay, and so you notice a few things kind of right away. Well, definitely the most money is being spent on TV. So that's where you see some really high values here in terms of the amount of money spent. But you also see, the radio and the newspaper effects. All of them look to be, well, spending money is at least a little bit helpful for everything. You sort of notice at least a weak positive trend, whereas you increase the amount of money that you spend, you also increase your sales for all three of these media. Even though for it's not, it looks more like a blob. That may be a little less clear. Okay, and we can use the describe function to just get a little numerical summary here. And what we see is that, yes, the mean for TV is much larger than the mean for radio and newspaper. And also its standard deviation is a lot larger than the other two. So TV is dominant both in terms of the mean and the amount of variance. Okay. And I think I already said that. Okay, so some of the questions that we want to try to answer. How can we quantify the relationship between advertising and sales? Can we predict the effect of each ad media on sales? And is the relationship linear? And then more specifically, we would like to know which of the different ad media, TV, radio, or newspaper, are the most effective at generating sales, because that will inform us where it would be good to spend our money in the future. And also, are there any interactions between the different ad media? So maybe we shouldn't be thinking of these as independent variables, but maybe they are related in some way that affects their impact on the sales. But first, simple, and let's think about just looking at the effect of TV advertising sales. So we use the following linear regression model, and we want to model sales as a linear function of TV, so beta 0 plus beta 1 times TV. And so we can use the OLS function from stats models, and it's really nice when you have your data stored as a data frame. You can just, have a really simple call where you just say, okay, I want to predict sales from TV, and I'm looking in this data frame, my advert data frame, and these are the columns that I'm interested in. And so you want to do this OLS.fit, and then you can print a summary to see the result of the regression. So what you notice is a lot of different information, probably more than you want to look at. Some of the really important things you want to look at, though, are the R squared and this F statistic and p-value associated. We'll get into some of that in a little bit, but also what's the equation of the line? That's also quite important. That is here under this coefficient column. So here you see 7.03 for the intercept and 0.047 for the slope. So now you could write down the equation of the line exactly. Okay, and so add the line to our scatter plot or to a scatter plot of TV versus sales. So if we have a scatter plot of TV versus sales, the predictions associated with E values in the data set will be stored in the output of that OLS object. So if we look at add tb ols.predict, that's where all the y hats are stored, and we can plot all of those y hats. They fall along a straight line, and so that lets us visualize the regression line that was computed. You can also dig out specifically parameters, right? And you can also define your own line and add it to the plot, but this is a really easy way to get the plot. Okay, so we see that the intercept of the line is 7.03. And so what does that mean? How should we interpret these numbers? Can't you just plot the equation? Well, you can, yeah, but you would have to, just define x values and associated y values and then plot those. So you definitely can. It might be like, I don't know, 2 more lines of code to just write it out, but yes, indeed. And usually when you do it that way, you don't need to plot it as a scatter plot. You could just use the plot function with, a few points in there. Okay, so how should we interpret what the intercept number means? So the intercept here is about 7. What that means is that without any TV advertising, the model predicts 7,000 units that will be sold. The slope of the line is 0.0475, and so think of the slope as telling you the increase in your response variable that you will see for each additional 1 unit increase in your explanatory variable. So if you spend $1 extra on TV advertising, then you expect to sell 0.04 more units. It might be more helpful to think about it in terms of how many more units you would sell per thousands of dollars spent. So if you spent $1,000 on $1,000 more dollars on TV advertising, then you would sell an additional 47.5 units, according to the regression model. Okay, and so how do you evaluate how good a fit the line is? Of course, you can always plot it and see how, the eyeball check, if it looks like it's fitting the data well, but there's also a more objective thing that you can do, which is to look at the sum of the squared residuals. So like we discussed, these optimal parameters, slope and intercept are minimizing the sum of the squared residuals. These are our y values minus our predicted y values. But this in and of itself is not super helpful because it of course depends on the scale of the data and the units that we use, etc. So this is an important quantity, but we need to kind of reformat it in order to interpret it in a useful way. In our example, the sum of squared residuals is 2,102, but is this big? Is this small? Who knows? So a more easily interpretable number to evaluate the quality of a linear regression is the R-squared value. Okay, and you may remember, well, no, actually, I'll say that in a second. How should you think of this R-squared value? You should interpret the R-squared value as telling you the proportion of the variable in the response variable that is explained by the model. So in this case, where, let's see, the R-squared was 0.61, we would say that explains 61% of the variability in sales. Okay, and so we also have another comment. Eyeballing the chart, error is not linear. Yeah, eyeballing the chart one notices a few things. We have a nice scatter here, which is good, and it really does. If you think about kind of looking at the center or the mean for each x value, it really does look pretty linear, at least along this side. You see the variance around the line kind of increase as you increase TV, which is usually you don't want to see that in a linear regression, but there's not a whole lot that you can do about it. So we won't go into, there's actually a few assumptions that ideally you check when you do a linear regression to sort of help you know, okay, is this valid? But in the interest of time, we won't go to all of them, but one of them you'll explore activity for today. Okay. All right, so I sort of said, how should we interpret the R squared value? And this R squared value is directly relatable to the sum of squared residuals. So as we've discussed, we can define the sum of squared residuals by looking at the difference between our y's and our predictions. And that measures basically the total of the errors. And then we can also look at the total sum of squares, and this just measures the total variation of the response variable. And so we're interested in knowing how big is the SSR relative to the TSS. So it's their relative values that are informative, not their absolute values. And so we can define the R squared value as 1 minus the ratio between the sum of squared residuals and the total sum of squares. This will always be a number between 0 and 1. This will always be a ratio. This will always be a percent. And so it's very useful for interpretation and for comparing across a lot of data sets. Okay, so here we have 0.61, so about 61% of the variability in sales. Okay, and you may remember back when we were talking about statistics in the beginning of the course, we talked about the correlation coefficient, which we wrote as a little r squared. And it turns out for simple linear regression, this capital R squared and this little r squared are exactly the same thing. So for simple linear regression, what we're doing here is simply computing the linear correlation coefficient between the y's and the predicted y hats. But when we start to deal with more complicated regression models, then that equivalence is not true anymore. And so we want to start thinking about this capital R squared a little bit more generally so that we can generalize it more easily to more complicated regression models, which we'll do in the future. Okay, so in here we have our fun little comic. I don't trust linear regressions when it's harder to guess the direction of the correlation from the scatter plot than to find new constellations on it. Yeah, that's pretty cute. Okay, and so as I mentioned earlier, you can also do linear regression in scikit. So that you can, and I'll just kind of go over the exact same thing in a different way so you can see it. So if you use the linear model.linear regression function, this creates a linear regression object. And one thing that's a little bit annoying if you're working with pandas data frames is that this linear regression function is not set up to input those data frames directly into that function. So you have to kind of reshape them to get them in the right format. So here, we're just extracting the values and then reshaping if necessary. And you can see here, I printed this out. So you can just kind of see what the input should look like. The input should look like this kind of array. This is like a NumPy array, which it requires as the input. And then once again, make our scatter plot, and we get the same picture here. And again, the predicted values are stored in lr.predict, just like what we did with stats models. Okay, so now let's talk a little bit about hypothesis testing in linear regression. So you may have noticed as you looked at the output of some of those regressions that there are some p-values and some test statistics. So let's talk a little bit more specifically about what's being computed there. Okay, so in descriptive statistics, one just seeks to describe the data. And so from that perspective, you might just be interested in the equation of the line of best like we have computed so far. But the statistical inference way of looking at this problem would be to think about it in the following way. So we suppose that there is a ground truth population with X and Y related by Y equals beta 0 plus beta 1X. So we suppose that there is some population parameter beta 0 and population parameter beta 1 that are the ground truth for the population, but that we don't get to observe directly. Rather, we sample a noisy version. So we sample data points xi, yi, where yi is generated according to that ground truth according to that ground truth formula, but plus noise. So we have sort of the prediction formula plus noise. Our data is corrupted by noise. We can think of these little epsilon i's as being random variables with a normal distribution, which we think of as the error of the observation. And we want to infer the values, the true values of beta 0 and beta 1 in the population from this noisy data that we observe. This is kind of the classic linear regression model, where you sort of model this as a line plus Gaussian noise. Okay, and so this gets into the same kind of setup as we were talking about in our lecture on hypothesis tests, where we were thinking about whether the coin was fair. We had a sample proportion of heads, and we used the central limit theorem to say that the variance, or standard error, decreased with the sample size as sigma squared over n. We didn't use the word standard error, but you can think of the standard error as essentially being the standard deviation that arises when you're approximating a quantity from sample size n. Okay, and so using this value and assuming the null hypothesis that the coin is fair, we could evaluate the likelihood of obtaining a sample as extreme as the one obtained. And so we're doing a similar setup here. In this context, our null hypothesis is beta 1. Remember, beta 1 is the slope. Beta 1 equals 0. That means there is no, I think I should have said linear relationship here. I'm sorry about that. This says there is no relationship between x and y. More correctly, it would be to say there is no linear relationship between x and y, and the alternate hypothesis that there is a linear relationship between x and y, i.e. beta 1 is not equal to 0, because really in this hypothesis test, we're not testing for all possible relationships between the variables. We're testing for a linear relationship, so that should be stated in the hypotheses. Okay, so we assume that epsilon is a normal random variable, say with 0 mean, right? So we want to see equal scatter above and below the line of best fit, and variance sigma squared. And so using similar ideas, you can work out standard errors for the intercept and the slope. We won't go through the derivation, but at the end of the day, you get a test statistic, which you compute from your sample slope and your standard error of that sample slope. And it has a t-distribution with n-2 degrees of freedom. And so the p-value is then computed from that t-distribution. And it's the same interpretation. A small p-value means that there is significant evidence for the alternate hypothesis, i.e. that there is a linear relationship between the explanatory variable and the response variable. Or if the p-value is large, then there is not evidence of a relationship between the variables. Okay, and now we have a good question in the chat. How likely is the error Gaussian? Right, so good question. Yeah, that's kind of a hard question to answer. So this is very common in statistics to set up these kind of models under an assumption of a Gaussian error and then derive a lot of theory based on that assumption. At the end of the day, you should check options. So if you're doing linear regression, you probably want to explicitly compute your errors and kind of see if they have a normal distribution. That is definitely not always satisfied for real data. Sometimes it is. I would think most of the time it isn't. And in that case, it can be a little difficult to know what to do. Sometimes the transfer data could help, perhaps, to try to get the residuals better behaved. That's a good question, and I would say, most of the time that assumption is not perfectly satisfied. Okay. And yeah, so in here, and let me just go back to the scatter plot. And what we see here, we see also sort of as we move across the plot, that the residuals, the errors, become bigger and bigger. So they don't look like they're identically distributed either. It looks like there is some spatial relationship there in the distribution. So I would say for that example, assumptions are not perfectly satisfied. But it can still be useful to do the linear regression, and this is still a good, nice fit for the data. Okay, so let's think about the following experiment. So before we go back and discuss the p-values that we computed for the advertising data, let's look at some synthetic data. So let's say we generate 100 random points according to the following model. Y is 3x plus epsilon, where epsilon is normally distributed with mean 0 and standard deviation 2. And let's say we call this one simulation, and we repeat this simulation 1,000 times. And each time we compute the best fit. Okay, so we can kind of look at what happens. So here we have a function f, which is our ground truth. And then I'm just defining some values here that will be used to plot the regression line. And here is our simulation. So we're going to do 1,000 simulations. In each simulation, we're going to sample 100 points. We're going to compute the line of best fit after we make our data noisy. And then we're going to plot, we're going to do a linear regression and compute the line of best fit. And we're going to plot that line of best fit and also sort of collect all of the slopes together in a vector here. Okay, so what do we get? You may want to look through this code in a little bit more detail when you have time. But we can see here this this black line is the ground truth, and then these red dots are just the plot from one of the simulations. So this is what a typical sample of data looks like. And then all of these different blue lines are the lines of best fit that were computed from all of the different samples in the different simulations. So how are we thinking of this? We're thinking of the blue lines as an approximation of the black line, of that ground truth line, but it's not going to be perfect, right? The black line has the exact intercept and slope of the population. A blue line that we compute from a sample will be a little bit off of that perfect black line. And so here we can see a histogram of values for all of the different slopes computed, and they are definitely centered at 3, so that's good. So they're the expectation is right. They're centered at 3, but there is a bit of variation here, ranging from about 2.4 to 3.6. So we could get unlucky in our sample and be a little bit off in our computation of that slope. Okay, so now let's return to the linear regression model of sales on TV advertising, right? So sales equals intercept plus slope times TV. If we look at the stats model output, we can see that the p-values for both the intercept and the slope are very small. So the probability of obtaining these values, if the null hypothesis is true, is nearly 0. So, so we reject the null hypothesis and we say there is evidence of a linear association or relationship between TV and sales. Okay. Let me see. Are there any questions on that up to this point? Any other questions?
Can you calculate a confidence interval?
Yes, you can, and it gives that to you. So if we scroll up to back up to the output, you notice right here, this is giving you a 95% confidence interval. So for that example, we could say the slope for the regression model with TV and sales, we're 95% confident between 0.04 and 0.05. Yep, so that's also helpful to look at the confidence interval. Any other questions?
Huh? Make sure we're taking a break.
Okay, well, why don't we go ahead and take our 5-minute break and come back at 1:10. Sound good to everybody? I'll see you back at 1:10. Okay, let's pick it back up. So, of course, you'd be interested in exploring the data set more generally. What about the other advertisement methods? So we looked at TV, but what about radio and newspaper? And let's repeat the analysis. So first of all, predicting sales from radio. We'll do the same OLS function. What do we see? An R squared of 0.33. And then the p-value that you want to look at is right here. So here's the test statistic, and here's the p-value associated with the intercept and the slope for radio. So this right here is the p-value of interest, which you see is is 0. And there's a confidence interval for the slope. Now we can repeat the same thing for newspaper. Here we get a really small R² value of 0.05. And however, when we look at the p-value associated with the significance test for linear association between newspaper and sales, we do see significance. It's still 0.001. So that's kind of interesting, especially with a large sample size. You can get a significant relationship even with a very, very weak association, right? This is only accounting for 5% of the variance in sales. So, you know, don't sort of, I guess, overestimate the usefulness of getting a significant p-value. It may still not be a super useful predictor. Okay. Okay, and then we can take a look. Once again, we can plot the 3 scatter plots like we had before. And now we can add on top the predictions as computed by the ordinary least squares regression, which are stored in this OLS.predict. Okay, so what conclusions should we draw here? The most effective advertising media? Well, does anybody have any comments? If you were going to spend more money, would you pick TV, radio, or newspaper, and why? Maybe someone wants to answer without reading the answer further down.
So I would say that per dollar spent that you get more sales for, it looks like both radio and newspaper versus TV. It looks like TV is more expensive and it doesn't quite get as much return per dollar spent. And it looks like radio is like the best.
Yeah, I think there's thank you. I think there's a very good case to be made for radio. So as you correctly pointed out, it has the steepest slope. So the slope is predicting that you are going to, the regression line is predicting that you will see a larger income by spending more money on radio. But there are some other things to keep in mind. You know, the R² of this linear relationship was only 0.33. This one was like 0.61. So this relationship is stronger. You might be more confident of the effect of spending more money on TV, even if it's smaller. Maybe it's less risky in some ways. But still, given the steepness of the slope here, you might want to go with radio. Newspaper is definitely not a great option because the association was so dismally low that even though you got a nice slope there in the regression line, it did the data very well.
I was gonna say it looks like you have a higher bias with newspaper, so that means that basically your whole graph is offset more. So how come that isn't a factor?
Oh, so what do you mean by bias in that case?
Bias is
you mean
your beta 1.
So you're saying, can you repeat that again? What about the slope?
Nothing. I'm sorry. Is beta 0 the interceptor? Is at beta 1? That's your bias. Is your intercept?
Oh, yes. Okay. Yeah, the beta 0 is the intercept, and you're right that for newspaper it is the highest. And I think that's partially because the slope is so small that the money spent on it is not having a very strong effect. All right, so we've kind of so far been thinking about, okay, well, which is the best predictor? But you don't have to use only one predictor. And so usually we can get a lot better model if we think about predicting sales from, all of the information, all of the data that we have. So maybe we should think about constructing a model that looks like the following, that's still linear, but it's linear in 3 variables, not just 1 variable. So we might model sales as sum intercept beta 0 plus beta 1 times TV plus beta 2 times radio plus beta 3 times newspaper. And this is the idea behind multiple linear regression. We're still modeling a linear function as generating the response variable, but we're thinking about multiple variables in that linear relationship. Okay, so let's try it here and see what happens if we try to model sales as a linear function of TV, radio, and newspaper. So you can do this with the OLS function in almost exactly the same syntax as before. Notice you just want to put in here whichever variables you want to include. So here we can say TV plus radio plus, or if we just wanted to do TV and radio, we could just say TV plus radio, whichever ones you want to use. And now we can look at the summary. So the R squared has gone up to about 90%. And so that's substantially higher than the R squared of any of the individual models, right? The highest was TV with 1 before, so now this is up at 0.9. And then when we're doing a multiple linear regression like this, it's really useful to, well, first of all, you're going to get a slope associated with each of your variables. Here's the slope for TV, radio, and newspaper. Notice the one is actually negative, so that's not promising for newspaper. And then you get a p-value associated with each of these slopes. And for TV, we see a p-value of 0, but you'll notice now for newspaper, we have a really high p-value of 0.86. And so this is telling us that this variable is not really contributing anything to this model, that we might as well just throw it out, okay? Because this p-value on this coefficient is so large. Okay, so we can make this. Yeah, go ahead.
This is just about the syntax of the Python code for the last example. So when we have in the sm.ols inside the parameters where we have formulas equal to sales tilde, is this like, I guess I was confused about the syntax. Are we putting our dependent variable first and we're saying it's supposed to be like as a function of these other variables? Is that how it's supposed to be interpreted?
Yes, correct. That's right. So dependent variable first, tilde, and then you can just write your independent variables that you want to consider with the plus signs. Now, of course, in practice, this is going to be introducing a coefficient on these variables. We don't write that, but this is just a quick way to tell it which variables to use.
Okay, thank you.
Yeah, no problem. Right. Okay. And indeed, here, and we also had a question in the chat, which is why sum? And I guess that was just like, why are we summing these things together? I will say that's just like the simplest place to start, but we'll see at the end of the lecture that we may want to do some more complicated things too. Okay. This is kind of the simplest. This is actually, well, this is the only linear and we can write for the response as a function of the predictors, but we may want to do a more complicated relationship, which we'll discuss later. Okay, So we see here that this p-value for newspaper is large, indicating that this variable is not contributing anything to the model. So you may be a little confused thinking, well, when we just looked at sales in newspaper, we got a significant p-value. So how come when we do this joint model with all three variables, it becomes insignificant? And so the thing to keep in mind there is that variables can be highly correlated with each other. And so when we are looking at a group of variables together, their significance may be different than if we looked at just one variable at a time. And that's because variables can be highly correlated. But in general, this is telling us that if we already know information about TV and radio, additional information from newspaper is not helpful. Okay, and you can again interpret the slopes in the same way. So spending an extra $1,000 on TV, you should sell about 46 more units, and spending an extra $1,000 on radio, you should increase by 18 more or 19 more units. So again, the steepest increase is occurring here for radio. Okay, and you may notice, okay, we have these individual p-values, which are telling us the significance test for, TV slope is 0, radio slope is 0, newspaper 0, but then there's also another p-value up here that corresponds to this F statistic. And this one is a joint hypothesis test where the null hypothesis is that all of those slopes are 0. So the null hypothesis for this F test is that beta 1 is 0 and beta 2 is 0 and beta 3 is 0. And the alternate is that at least one of them is non-zero, that there is some kind of linear association in the data. So that can also be helpful to look at, but a little more helpful is to kind of analyze the effect of the different variables. Okay. Okay, yeah, so I think we got all of this. And we talked the fact that, why are we getting the low p-value for newspaper when we had a high p-value before? And it's because newspaper is a confounder. And so it can be really helpful to look at the correlations in your variables when you're doing a linear regression like this, so that you're aware of the relationships between the variables. So recall that we defined the linear correlation coefficient between two variables x and y in this way, and it's always between -1 and 1, and it varies, how much the two variables tend to take on, how much they vary together. So look, for this data set, we can do this, first of all, just print this correlation matrix, and then we can also do a plot of the scatter matrix, where we can visualize all of the different scatter plots between all these combinations of different variables. So we can see here the pretty strong relationships here between TV and sales, and also between radio and sales. And then also, I don't know that I would say it's like a real correlation, but there is a correlation between newspaper, right? Newspaper and TV, and some here between, what is it? Between newspaper and TV, actually, those are not very well correlated, but between newspaper and radio, that's where you see somewhat of a substantial correlation. Between newspaper and radio, you have a correlation of 0.35. So that kind of explains why when you looked at newspaper on its own, it appeared significant. But when you do a model that has all of the variables, you see that it's not contributing anything additional if you're already using radio and TV. Okay. Right, so the influence of radio on sales can be incorrectly attributed to newspaper advertisement. Okay, so basically going through this process, we can see that since the newspaper's not really contributing anything, we should take it out because we want as simple a model as possible that still is a good predictor for the data. And so this would be the best linear model, just using TV and radio. And so if we rerun the regression with just those two factors, we see the R-squared value has not changed. It's still about 90%. And we see that both of these variables are significant predictors. Okay. Okay, and then here we can also plot, here we have a regression surface, right? So before we had a scatter plot and we were trying to find the line of best. Now we've got two variables. And so we are computing a plane, sort of the plane of best fit through this three-dimensional point cloud. So just kind of keep this visual picture in mind that this is what we are doing. So here you've got a scatter plot of the data, and then superimposed over it, you have the plane of the predicted values. And you can look back here at the code to see exactly how that's generated. You know, first you kind of initialize these 3D axes, then you add the scatter plot, and then you define a grid of values, a grid of XY values, and then you pull out the parameters from the model, define a dictionary with those parameters, and then you can just, so this is just kind of manually creating the predicted values by explicitly writing out the equation. And then you can do a surface plot, and this parameter will make the surface a little bit transparent so you can see through the surface and still see the data points. Okay. All right, so let's, in the remaining few minutes, and we did have an activity for today, so hopefully I can finish this in like 5 minutes and then we'll still have some time for our activity. Let's discuss nonlinear relationships. So when do you want to, or when might you have a nonlinear relationship in your data? Well, the idea might be that these are not independent factors. They interact with each other. And so you shouldn't have a model for sales that just models these effects, but maybe you should also include a term that we can think of as modeling the interaction between the TV budget and the radio budget. So this might be known as a synergy effect, right? So maybe there's some kind of contribution where if both of these numbers are large, it creates a synergy and we get an even bigger boost. So they may have a nonlinear reaction in that way that we want to include in the model. But you can see that in terms of the math side of things, well, this looks just like the model that we did before, except as our third variable, instead of newspaper, we have TV budget times radio budget. So we can just construct this explicitly. So you could construct a column that has that product in the data and then do linear regression on TV, radio, and the product. But the OLS also has this functionality built in, so you don't even have to do that. You can just call this model with TV plus radio plus TV times radio, and it will create this third variable, the interaction TV and radio. And what you see here is actually you get a nice advantage, nice benefit from doing this. So the R squared increased from 90% to about 97% by explicitly modeling this interaction term. And if we look at the p-value for the interaction term, it is again significant. Okay, so we've really found actually a really good model for the data. We've got these two variables and we've got their interaction, and altogether it's generating an R squared of 97%, and all significant, and all the coefficients are significant in the linear regression. And so here, once again, it's the same kind of plot where you can the 3D point cloud and then plot the surface on top. It's no longer a linear surface, right? It's got a little bit of a curve to it, but you can see that this fits the data actually a lot better. So you see as it kind of, it kind of goes up here. And if you compare that with what we had here, you can definitely see it's fitting this upper data better. Okay. And yes, so I'll let you look at the comic, but there's lots of I guess one thing that we'll talk about, and we'll talk about this more in the next lecture too, is we want to be careful about overfitting our data, so we can always generate a better fit to a data set by including more independent variables. But we basically, it's important to find the simplest model that does a good job, because that will generalize better to new data that we haven't seen before. And we'll talk a lot about that next time. But I think, are there any more questions before we start the breakout rooms and you can do the little activity? Okay, so I'm not hearing questions from anybody. So let me go ahead and do the breakout rooms. And let's go with, okay. All right, so so enjoy the activity. Let me know if you have any questions, and I'll see everybody on Thursday.
Hello, I had a question.
Yeah, hey.
So for the first activity where we're plotting the scatter plot,
Mhm.
and X is the dose and Y is the food consumption,
That's right.
how are we supposed to, like, with the three lists that we were given, how are we supposed to identify X and Y?
That's right. So the list that you were given, I mean the Y values, and so each of those shares one of the X values. So like, so there's only three different X values because in the experiment they either got 0, 2.5, or they got 5. So basically you have to create that.
Okay.
So you're going to need to create a vector of those X values, that's like 0, 0, 0, 0, 0, 2.5, 2.5, 2.5, that repeats as many times as necessary to match the dimensions of the Y values. And the Ys you'll need to concatenate into one vector, so you have like one vector of all your X's and one vector of all your Ys.
Okay, that makes sense. Thank you.
No problem.
I have a questions as well, if that's okay.
Yeah, sure.
So for number one, we have to do the equation, and I just wonder, like in this case, how when I do the OLS function, which of the I think you probably already said in class, but which one is the beta naught and which one is the beta 1 from the table, or is it not really given from the OLS function? Is that something we have to identify?
Yeah, if you print the summary, it will tell you that. And you'll see it's like it's easier to identify when you've named your columns like the appropriate names.
Uh-huh.
So I'd have to see like what your output is exactly, but here I can share my screen and go back to.
Can I? Oh, okay.
Or yeah, no, go ahead. Did you get it?
I was just gonna share from the lecture that we have. So like this one, right, that you have.
Mm-hmm.
And so this intercept. So this is B naught, right?
That's right. Mm-hmm. That's
But which
beta naught.
one?
And the 0.04 is the beta 1. So it's in that first column there, right? That's
okay.
that's 0. The 7 is the beta 0, and the 0.047 is the beta naught.
Okay.
So you want to look at the coefficients column. The coefficients column is telling you what the coefficients should be to actually write down the equation.
Oh, okay. And that's the B naught. The coefficient is B naught. Understand that error is the B1.
No, no, B1 is not standard error. B1 is the coefficient of TV, the number right below the one you highlighted.
Okay, I see.
Yeah.
Okay, thank you so much.
Yeah, you're welcome. All right, since we're over time, close the breakout rooms. So they will be closing in 1 minute.
Is Professor Little gone?
Are we supposed to just leave?
I think we probably can. I just want to ask her a question about this activity.
Did anyone else get a graph that actually?
I'm not sure what to put in as the X or on the X-axis.
Yeah.
Yeah, that's what we're too.
I think she said that you have to create.
Okay. Okay, I'm going to ask one. Okay. If we get muted again, I'm just going to go to my next class. So I just wanted to quickly ask. So what did someone was saying something?
Oh, I was talking to her and I think she said that you have